Let's discuss today's problem. So it really takes me a lot of time to solve this problem. It's division 2 problem E and its rating is 2200. So let's begin. As always, we are going to introduce the problem by explaining the example here. So we are going to choose an easy example, this one, all right? So in the input, we have two numbers here. The first number is the number of antennas in the test, right? And the second number is the distance we are going to cover. So what does that mean? So this is our distance we need to cover, right? And we got two antennas in the beginning. The first one is at this position, 20, right? And the initial range of this antenna is 0. So this antenna can only cover this integer, number 20, right? And the other antenna is at position 3, and its range is 1. So it can cover position 2, position 3, and position 4, right? This 1 is this antenna's range, so it can cover the two positions that are next to it, right? If its range is 2, then it can cover furthermore, right? So the question of this problem is that we can extend the range of any antennas. For example, we can extend this antenna to 2, for example, right? So it can cover 1, 2, 3, 4, 5. And we can extend any number of range and any number of antennas. So the question is that if one extension's cost is 1, then what's the minimum cost, right? For example, if we extend this antenna to 2, right, range 2, and extend this antenna to range 30, right? So this guy can cover this place, can cover this whole place, right? And also can cover this whole place. So this antenna can cover from integer 1 to integer 50. So the total cost is 30, right? Because we extend this antenna's range from 0 to 30. So its cost is 30. So that is the mean cost in order for us to cover the entire distance, right? So um, can we find a smaller cost? Let's try it. So let's try to extend this antenna to cover the whole distance, right? So in order to cover this part, we need to extend this antenna to 47, right? And for the left part, of course, we can also cover it if we already extend this antenna range to 47. And the initial range is 1, so the total cost is 46. So after use $46, we can cover the whole range. But 46 is bigger than 30. So 30 is still the minimal cost, right? So I can assure you that for this specific case, 30 is the minimal cost, and the solution is just to extend this antenna to 30, right? And how do we find the minimal cost? So we are going to use dynamic programming, right? So for dynamic programming problems, the most important part is to figure out the definition of each state, right? So we are going to calculate Fi. What's Fi here? Fi is, let's say, we have a distance to cover, right? And we are going to, from left to right, we are going to calculate each um, f for each integer, right? So the f's definition is that the minimal cost to cover from 1 to I, right? So the definition here is the mean cost to cover from 1 to I, right? So what's the mean cost to cover 1, right? So for in this case, it's just um, extend 3 to um, the antenna at position 3 to this place, right? So the extension cost is 1, right? Because this guy is already covered, and we can just extend it to here, right? So the F1 equals to 1. And what's the mean cost to cover 1 to 2? So it's still 1, right? Because we already have the position 2 covered, so no more cost. So what's the minimum cost to cover 1, 2, 3? Is still 1, right? Because position 3 is also covered, right? Etc. So how do we calculate Fi? So the formula to cover the formula to calculate Fi is here, right? So let's say we already calculated Fi F1 to Fi plus minus 1, right? Because we calculate all these numbers from left to the right. So at the time we are calculating Fi, we already calculate all these numbers before Fi, right? So we already know all these numbers. And how do we calculate Fi based on all these numbers? So this is our solution, right? So for the number I, we must have at least one antenna cover it. So let's iterate each antenna, right? So xj is the position of the number j antenna, right? Let's say this antenna is here, right? So we are going to try this antenna. We are going to use this antenna cover the position I, right? And let's say uh, um, we have a this antenna's range is from xj to here, right? Its range is sj, right? It's already in the input, right? xj is this number and sj is this number, right? So if we are going to use this antenna to cover this number, how much do we need to cost? Is I minus xj plus sj, right? This is how much it will cost us, right? Because the farthest position we are going to reach is this position, and we are going to extend I minus this position. This is the delta, final delta, and it's also our cost, right? And this guy will add to the cost, right? And how what is the cost to cover the numbers come before I? So because with this antenna start from this place to this place, so these numbers are already covered, and also this antenna already covered this place, right? Because we extend this antenna from here to here. So correspondingly, it also will cover here to here, right? To its left side. So all we need to care is about how do we cover this part outside of this antenna J, right? So what's the minimal cost of uh, what's the minimal cost to cover this part is here, right? Because this position is x this position is xj minus I minus xj, right? So it's essentially the mirror point of this I, and the center is here. So uh, this this distance is I minus xj. So xj minus this distance equals the position of this guy, right? And the minimal cost of covering this distance is f this number, right? We already calculated before. That's how we use the previous calculated states to calculate the current state, right? So that is our first case, first scenario. So in this scenario, the I is here, and the antenna is at the left side of I, right? So we can use this algorithm to calculate it. So what about the antenna is at the right side of I, right? It's like this, right? So we can also solve this kind of scenarios, right? So we need to break it into two scenarios. The first scenario is that this antenna is already covering I, right? It means uh, this is the range of the J antenna. So this range already cover I, so that our best case scenario is to um, just use f x j minus sj, right? So this position is essentially this number, right? xj minus sj, right? So we can find the xj is its mirror point to the left side. I mean, we can find out the position where this antenna can reach, right? This is the farthest position this antenna can reach. So we can just find out what's the minimal cost of covering this range. So it's here, and we add it into. Actually, we don't need to add anything because this is the initial range of antenna J, right? And the antenna J already cover I and also cover this whole range. So the minimal cost of covering the whole range is just the minimal cost of this range, right? So we can just choose a maximum, choose the minimal number of fi, and this this cost, right? So that's the first scenario. Let's look at the second scenario, where you have a I here, and you have a antenna here, and the initial range of the antenna is here, right? Is still to the right side of I, right? So we already covered this place. So we need to extend the range to here, right? So the cost is how much? What's the cost here? Is x minus s, then minus j, right? That is the delta. That is the cost here. And after we cover all this place, we need to also cover the distance before it. So how much? What's the minimal cost of what's the minimal cost to cover this place? Is f I minus 1, right? By definition, the minimal cost the minimal cost to cover this distance is fi minus 1, right? So we got fi minus 1 plus this value, right? Actually, here is I, should be I. That's a typo, right? So that's it. That's how we calculate all of those fi. So after we calculate all of these fi's, so fm means what's the minimal cost to cover from 1 to m, right? That is the final answer here. So I guess that's it. Let's look at the code here. So in the code, there is nothing surprising here, right? So just read the xi, the location of antenna, and the range of antenna. Then um, this 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 guy here is quite interesting. So actually, I'm going to dive deep into it, right? So before we get into the code, we need to find a edge case here, right? So what if we have a antenna here? Um, and the F1 here, the F1's value here is to extend this antenna to this place, right? So let's say its cost is 5. So F1 equals 5, right? So let's take a step further. So let's calculate F2 here. So F2 here will also use this antenna to cover it, right? So its cost is 4, obviously, right? And after we extend this guy to here, we also need to add F1 into the final answer, right? So that the final answer is F1 plus 4 here. This is wrong because in this way we extended this antenna twice, right? One is for the first position and the second time is for the second position, right? So we extend this antenna twice. So how do we avoid this problem? So at the beginning, we are going to add a antenna at position 0, right? And this antenna's range is also 0. So in this case, so let's see what has been changed. So we still have a antenna here, and we have a antenna at the position 0 and range 0. So the first F1 we calculated is how many? Is instead of 5, we're going to have 1 here, right? F1 equals 1. And F2 equals F2 equals 2, right? Because the best way to cover 2 is to extend the antenna at the position 0 instead of extend this guy to here, right? So at some point, to cover this place, we better to use this antenna, like extended by 1. And to cover the integers before it, we are going to use the antenna 0. The antenna we added, right? So in this way, we can be sure that no antenna are going to be extended twice in the problem, right? So in this way, we can be sure the final answer is minimal cost. And why can we add extra antenna into the game? How can we add a random antenna into the problem without affecting the final answer? The reason is that the optimal solution will never choose the antenna 0 to extend, right? Why? Because, for example, you have 1 to m to cover, and you got a antenna here, right, at a position 0, and you have a antenna here. So which one are you going to choose to extend? Of course, this one, right? Because if you choose this one to extend, uh, the the cost will all be used to extend its right side. You have no use of its left side, right? So it's better to extend this antenna instead of the antenna 0. So if we add antenna 0 here, and we calculated a optimal solution based on the new problem, this optimal answer will be the same as the optimal answer without the antenna 0, right? Because antenna 0 will never be chosen to extend, right? So that's why we in the code we use um, this initial. Actually, this should be changing to I, right? That's why we initialize if I equals to I, right? And the following part is just calculate each I, right? And for each I, we're going to use each of the antenna, and we are going to solve Fi based on the its special scenarios described here, right? And the why we use maximal here is just to ensure that the antenna's cover range is um, so let's say we have a antenna at position 3 and its range is 5, so it will exceed the range we are going to cover, right? So this guy is to just make sure that we don't exceed the range, right? And it's the same as this guy, right? So the rest are the same as described here, right? So I guess that's it. Thank you for watching.